Welcome back. We're still looking at revising redox reactions. We shall look at a couple of more examples and see how best we apply what we learned in terms of the redox reactions. All right, so at the back of our mind, we also need to remind ourselves of what is important in terms of representing, these redox reactions. In representing redox reactions, we need to have two half reactions, okay, which is the oxidation, okay, which has to do with the loss of electrons, as well as the reduction. So we call these half reactions, okay? And then the net ionic equation excludes the spectators. But what are spectators? These are species or substances that are not involved in the transfer of electrons or in the redox reaction for that matter, okay? And then a full balanced chemical equation is a combination of the two half reactions. That's in as far as representing these redox reactions. Right. Now, when it comes to balancing, what are some of the important points to remember? First of all, we must keep track of the oxidation numbers by applying the rules of assigning oxidation numbers to substances, in a reaction. And also, half reactions are actually derived. We can take them from the standard reduction potential tables. But on that note, remember, when we talk about the standard reduction potential tables, all these reactions are written in the form of gain of electrons. So by comparison, depending on the two substances that we are actually focusing our attention on, we can then decide from that point as to which one is a stronger reducing agent as well as which one is a stronger oxidizing agent. Then we are able to extract what we would refer to as those two half reactions in terms of oxidation as well as reduction. Right. So the importance of the standard table of standard reduction potential table cannot be overemphasized therefore. Right. So here is another typical question which says, consider the redox reaction which is given below. So the moment it says a redox, let's think of it in terms of electron transfer. Right. Okay. Let's think of it in terms of electron transfer or transfer of electron, which has to do with loss as well as the gain of electron. Okay, so that schematic representation becomes very, very key. So it says here, write down the formula. I'm going to underline the term formula of the reducing agent. First thing first, we need to understand what is the role of a reducing agent in a redox reaction. But by so doing, we need to keep track of the oxidation numbers. So iron 3 is 3 plus, is plus 3. Zinc as an atom, it's 0. This side ion is 2 plus, okay? And then zinc is also 2 plus. So a reducing agent is actually a substance that undergoes the loss of electrons, oxidation. So there needs to be an increase in the oxidation number, right? So a substance that undergoes the loss in this case is zinc. So the zinc metal, according to the equation, Zn, okay, to give us Zn 2 plus 2 electrons. So this is the substance that loses electrons. It is a reducing agent because it underwent oxidation. So the formula, therefore, is zinc, Zn, right? So sometimes it can say the name. If it says the name, then you have to write the full chemical name. But in this case, we're looking at the formula, right? Okay, and then write down the equation of the reduction half reaction. Okay, reduction has to do with the gain of electrons. So if a substance gains electrons, what happens to its oxidation number? We have said zinc loses, meaning that the other species, which is iron 3, which changes its oxidation number to plus 3, from plus 3 to plus 2. So there is a decrease in the oxidation number. Hence, this substance has gained. So the half reaction that's relevant is going to be iron 3, okay, plus an electron to give us what? Iron 2. Okay? So this is the equation, but the substance that undergoes the reduction process in this case is iron 3. Right. Pay careful attention to that. Okay? Now, the question goes on and says, write down the equation once again of the oxidation half reaction. So the equation represents a process in which substances either lose or gain in the entire transfer of electrons. So you'd want to understand it in that way. So a substance that undergoes oxidation actually has its oxidation number increasing, okay? Because that is coupled by the loss of electrons. Exactly how do we represent that? We are saying that for oxidation, we want a substance whose oxidation number increases. We have identified that zinc, according to the laws of assigning oxidation numbers, as an atom, it's got 0 oxidation number, then here it's +2, right? So what has happened here? Zinc has lost electrons. But then how do we represent that? Because that's what the question demands of us. We are saying it's Zn, okay, to give us what? Zinc, okay, let's just correct that. Okay. So be careful when you write, the chemical formula must be correct as well. So this is zinc 2 plus 2 electrons. So you realize that we are consistent that in the oxidation half reaction, the electrons are always on the right-hand side of the arrow, right? So this is what represents the oxidation half reaction, right? And then use the two half reactions to write a balanced net ionic equation. Emphasis in this case is on the balance, right? So if we go to our two half equations, what do we have? We have identified that for iron to be reduced, its oxidation number, it changed from +3 to +2. It means it gained electrons. Hence, it can be explained with respect to the reduction half reaction. While zinc, if we keep track of the changes that happened in terms of the oxidation number, it's 0 to +2, right? So what exactly happens to zinc atoms? Zinc atoms were involved in the loss of electrons, which can be represented using the oxidation half reaction, right? So the loss of electrons is oxidation, gain of electrons is reduction. But remember, if a transfer does take place, whatever species A loses is the same number of electrons that species B will gain in the case of electrons being transferred between A and B. So in this case, the number of electrons lost by zinc atoms must be equal to the number of electrons that are gained by the iron 3 ions, okay, in that transfer. That's the long and short of it. So in this case, to actually balance the electrons, it says this one will multiply by 1 and this one will multiply by 2. So you'd realize once we do that, we are able to eliminate, in a way, the electrons such that it will have the same number of what? Of electrons in terms of loss and gain. So if we multiply zinc by 1, we'll have zinc, okay, plus, okay, 2 Fe3 plus. Remember, we're multiplying the reduction half reaction by 2, right? Plus, this will give us, because the electrons will be the same, 2 for oxidation and 2 for reduction. So we can kind of eliminate them. So if we multiply this by 2, it becomes 2, 2, 2. And then we are able to take that out, okay? That's why we don't, in the net ionic equation, we don't include the electrons. Then this gives us zinc, 2 plus, right, plus 2 iron 2, right? So this is our overall, or the net ionic equation in as far as this is concerned. So there's a lot of knowledge that we need to remind ourselves before we actually arrive at a solution. Oxidation numbers, the rules for assigning oxidation numbers, the half reactions, and the technique, because this particular question focuses on the balancing part of it, which is a very, a critical component of redox reactions. Right. So having said that, I think we are able to then say, okay, there's quite a lot of examples, but this was just but one of the few that we have time to actually attempt. Right. For now, we'll take a short break, And then after that, we are able to look at even more examples. Let's take a short break for now.